All right, everyone, Mr. Graham here. Today I want to just tie together some of the things that we've been learning about these motion graphs. Some things that we should know at this point. On a position versus time graph, the slope is the velocity. A positive slope is a positive velocity, a negative slope is a negative velocity, which just means velocity in the opposite direction, in the negative direction. And we should know that the steeper the slope, the faster the object's moving, regardless of whether it's positive or negative. And that's what this term magnitude means. When we talk about the magnitude of a velocity, we're just talking about how fast it's actually going. It's actually the speed. You should know the difference now between velocity and speed. The magnitude of a velocity is just the speed. We don't care about direction. So if we have a velocity of negative 10 meters per second, the magnitude or the speed is just 10 meters per second. It's just how fast the object is moving. And also on velocity versus time graphs, you should now know that the slope is the acceleration. Same thing. Positive slope, positive acceleration, negative slope, negative acceleration. The steeper the slope, the larger the magnitude of the acceleration. It can be either positive or negative. Okay. But I want us to look at these graphs in a slightly different way now and consider the units. In your math class, y and x, unless you're doing a word problem where y and x actually represent something, you don't typically think of the units involved. But with our motion graphs, and here I got a position or a distance versus time graph, position slash distance versus time. We have units associated with these axes. And so our vertical axis represents our position, usually in the x direction, sometimes in the y direction. And we're going to measure that in the base SI unit for length, which is meter. And then the time axis represents, obviously, the passage of time, and the base SI unit for time is the second. And when we calculate a slope, we want to keep in mind the units and what they mean. So if I pick 2 points here, and then find the rise over the run, that's how we calculate slopes. And so here, my run is going across to the right. So the units for the run are seconds. Likewise, the units for the rise on my y-axis or my vertical axis, I'm plotting the position of the object, and so that unit is going to be the meter. And so when I calculate a slope here, I'm calculating a velocity, carry the units. The units will go along with the slope. So let's say that my slope here, the units are going to be the units of my rise, which is meters, over the units of my run, which are seconds. This is a nice way to see that the slope is telling you the velocity, because the units of our slope, the dimensions of our slope, dimension and unit kind of synonymous here, are meters per second. And that's one way that we can see that when I calculate the slope on a position time graph or a distance time graph, I get the velocity. And the same thing is going to happen whenever I deal with a velocity versus time graph. So let's pretend now, or let's assume now, that I'm dealing with a velocity versus time graph. Let's say I have the same type of graph. So I do have an acceleration. So the vertical axis will now be velocity in meters per second. And the horizontal axis is still time. Now, so my run is still going to be in units of seconds, but my rise now is in units of velocity. And my unit of velocity is meters per second. And then I deal with the slope the same way. If I want to talk about the units of the slope on a velocity versus time graph, well, my slope is going to be the rise. The rise is in units of meters per second. And then my run is in units of seconds. There's a compound fraction. This is why sometimes you say the units of acceleration are meters per second. It's how fast you get fast. I can actually work this out a little bit. I can make the denominator. This is a compound fraction. I don't like compound fractions. So I can turn this into a single fraction by making the denominator a fraction itself, just by putting the seconds over 1. And so whenever you divide a fraction by another fraction, you multiply by the reciprocal. So it's times 1 over seconds. And so the units for my slope on a position time graph are meters per second squared. And this is the unit for acceleration. So hopefully that gives you a little more insight into what these slopes actually mean, or the reason that the slope on a position time graph tells you velocity and the slope on a velocity time graph tells you acceleration. Now, the last thing I want to talk about in this video We can get one more piece of information from any velocity versus time graph, and that is the displacement that the object undergoes as it's moving. And let's go ahead and let's consider an object traveling at constant velocity. Remember, if you're traveling at constant velocity, the velocity value itself on the vertical axis doesn't change. So if let's say that the object is moving at 10 meters per second. Well, at time t equals 0, we're traveling at 10 meters per second. At some later time, say 5 seconds, we're still at 10 meters per second, so we're traveling with constant velocity. Well, what happens if how can I get displacement from this graph? Let me show you. Let's say at some later time t, we'll just call it t, it could represent an actual number. I want to know how far this object has traveled, okay? Well, notice that the height, I have a rectangle here, right? It could be a square, but a square is just a rectangle. It's more often than not just a rectangle. So the height of this rectangle is the speed v, the velocity v. The width of this rectangle is the time t. And notice that if I was to multiply a time, which is in units of meters per second, and I multiply that times the run here, the units of the run here are in seconds. Those seconds cancel, and so my calculation, whatever the numbers happen to be, will give me a value whose dimensions or whose unit are meters, okay? Notice what I did here. I multiplied a velocity times a time. And on my diagram here, the height of this rectangle, is the value v. And the width of this rectangle is the time t. So what I can do is just find the area. The area the area between a velocity versus time graph and the time axis tells us the displacement. So if I have a graph, a motion graph, the area equals displacement. So that's another thing that we can calculate from a velocity versus time graph. Again, this is a velocity versus time graph. So I can actually put that in my list here. I can say that the area between the graph and the t-axis equals the displacement. If you're an on-level or pre-AP physics, then that's delta D. If you're an AP Physics 1 or AP Physics C, that's either displacement delta x in the x direction or delta y if we're talking about the y direction, okay? And it doesn't just work for constant velocity. If instead I had a graph that where I'm actually accelerating, the object is actually accelerating, then it would be linear on a velocity versus time graph. And let's say it didn't start at a zero velocity. Let's say it started at some velocity, say like 1 meter per second. So when we start our stopwatch, the object's already moving. Think of a rolling start in a NASCAR race or something like that. And then let's say that motion is going to continue for some time t. Well, the area still works. This is a trapezoid. If you remember your formula for a trapezoid, you can just use that formula for the area. I tend to forget formulas quite a bit. So what I tend to do is just divide this shape into a triangle. So I find the area of the triangle and I find the area of the rectangle and I add those together. And again, if I do that, the area will be the displacement. Did I spell that right? Yeah, I think so. So that's one other thing that we can get from a velocity versus time graph. We can actually get the displacement of the object. And not only does it work for a straight line, if you take AP Physics C or you just study physics at a higher level when you go to college, then when we have velocity versus time graphs that curve, meaning the acceleration changes, this still works. It's just that you need calculus in order to calculate areas between curved lines and the horizontal axis. Okay, so that's all I wanted to go over for today. Hopefully this kind of clears some things up. The take-home points are right here. These two things right there, you got to know those. You can answer many questions that you'll expect to see in the future if you just remember these things. The slopes, very important for both graphs. The area, very important for your velocity versus time graph. All right, that's about it.